All right, gang, Mass 6610, moving into two sample independent t-test. Now, this is something, I think I said in the last, well, I know I said in the last video that I'd never seen a one sample t-test reported in any of the, the, the studies that I've advised. That's true. I've seen many two sample independent t-tests reported. So, uh, the purpose of the previous videos about sampling distributions and central limit theorem and even the one sample t-test is really to get us to this point. So we're really starting to get into relevant tests that probably each and every one of you will conduct in your research project. So let's get to it. So imagine, staying true to the data set that I've used previously. Let's say that we have GRE and we want to see if there's a difference in GRE across students who have been admitted and those who have not been admitted. Now, the purpose of this may be, my daughters are currently applying to different colleges and universities, and some of them claim that they're going test optional. I question whether or not that's really going on behind the scenes. So this may give a little bit of insight to whether the GRE scores are different across those who are admitted with those who are not admitted. So the first thing we should do is pump the brakes and rewind a little bit and think about what does the sampling distribution look like. Well, first of all, we're testing under the null and alternative hypotheses that the means from the two populations are equal versus they are not equal. This is equivalent to saying that and this is really what our focus is, this is equivalent to saying that the difference in the means is equal to 0 or the difference in the means is not equal to 0. So you kind of have to frame the way of thinking in that we're really not testing whether the means are equal, we're testing the difference in the means, which is equivalent, essentially saying the same thing. And I will let you know, I've gone ahead and written all the notes out for this video because I found out that I don't write very well if I'm trying to speak. So you might say, well, Dr. Darbro, you don't write very well when you're not speaking. That would be hard to disagree with. All right, so kick in the central limit theorem. So the things we worry about with the central limit theorem is what does the distribution of sample mean differences look like? So imagine diving into population number 1 and pulling out a sample mean from population number 2, calculating the difference, and this is our first sample mean difference. Do it again. In the spirit of the previous videos, we end up with a whole lot of difference of sample means, and we call this the distribution of sample mean differences, or the distribution of the difference in sample means. The mean of this distribution, it turns out too that this distribution will be normally distributed. And why is that important? Because a normal distribution is defined by its center and its spread. Well, the center of that distribution, mu, because it's a population of the measurements we're taking, x bar 1 minus x bar 2, is just the mean of the population minus the mean of the population number 1 minus the mean of the population number 2. The standard error depends. There's some caveats here that we have to consider, and I'm going to teach you the difference, and then I'm going to tell you what I think you should do and the reason I think you should do that. So the first thing we have to ask ourselves is, do we have equal variances? In this case, we have two populations, so we'll have two variances, the variance for the first population and the variance for the second population, and are both populations normally distributed? If we answer, now first of all, are both populations normally distributed? Well, let's just assume for the moment that this is yes. So we're going to focus on, are the variances equal? Well, if we can say with absolute certainty yes, then we do what's called a pooled t-test, and the standard error looks like this. It's the square root of the pooled variances times 1 over n1 plus 1 over n2, that quantity. Where we can find, this is not correct, that should be a p, where the pooled variance can be calculated with this very simple formula. It looks kind of complicated, but it's really not. It takes the sample size minus 1 times the variance, sample size minus 1 times the variance over n1 plus n2 minus 2. So not a lot going on there, even though if you teach that to undergraduate students or maybe dual credit students, they tend to flip out on you. If we're working with an unpooled t-test, which we are not assuming that the variances are equal, we get a much simpler standard error. But as we'll see down here, the degrees of freedom can be pretty messy. In other words, you can always tell whether you're doing a pooled t-test or an unpooled t-test by the degrees of freedom. If you get a pooled degrees of freedom like 132, then you're doing a pooled t-test. If you get a degrees of freedom of 127.62, then you're doing an unpooled t-test. So I can always tell the type of test that a student has run just by looking at the degrees of freedom. And it turns out that these are really easy to do in R, so there's not a lot of struggle with. It's not really even a struggle, it's just a little bit time consuming. So how do we test? Well, as we'll find out with statistical procedures and techniques coming up, we need to test our assumptions, because deviation from assumptions are what leads us to get p-values that we think are stable when they're not stable. In other words, we do everything correct. We put it in R when there are no typos, there's no issues whatsoever. We type in the correct R code, and we get a p-value of 0.032. If we have violated the assumptions, then that 0.032 is not our stable p-value. That's a p-value that we get running on an assumption that assumptions have not been violated when they may have been. And it leads to type 1 and type 2 errors as well. So first of all, one thing that we need is the samples need to appear that they came from a normal distribution. Again, normal distributions are specific to a population. That mu1 and mu2 that we talked about back in the very first page, that would be a normal distribution. The samples that we pull from those distributions may be bell-shaped and symmetric, but they are not a normal distribution. So does it appear that the population from which we drew our samples are normally distributed? Next thing we want to do is we want to test for equal variances. Next thing, and this is by far the most important, it'll be a test question, I'm sure. It is by far the most important assumption of statistical tests. Now, once we get into repeated measures and dependent samples, t-test, and possibly even some mixed models, we violate this independence assumption, but we make corrective measures to overcome that. And our data needs to be at the interval level at least. If you're testing assumptions on survey data, then this procedure is not appropriate. We need, because again, Likert data 1, 2, 3, 4, 5 really don't stand for anything other than strongly agree. Again, more about that later. But just make sure that your data is at an interval level. So we're going to report the results, and this is what I'm going to do in the next video. I'm going to run through, just like I did with the one sample t-test. We'll run a priori power analysis with g-power. We'll calculate our test statistic, degrees of freedom, p-value, report that, report the CI, confidence interval, and calculate and report the effect size. The effect size we use here, Cohen's d, you can actually that we used previously. You can calculate that, but I typically just calculate R because it's a function of our test statistic, which is really, really easy to get. And this is just a criteria for deciding whether we have a small effect, medium effect, or a large effect. So what happens? What's the math behind everything? Well, first of all, under the null hypothesis, we assume that the difference is equal to 0. So we assume that we're drawing from this distribution, and we're testing versus the difference is not equal to 0. We calculate the test statistic, which should make sense to you at this point that this is the estimate, minus the claim in the hypothesis, the null hypothesis. This is actually 0, right? So we're claiming. So it's, essentially the numerator is just x bar 1 minus x bar 2, divided by the standard error for this. Now that depends. Are we conducting a pooled test or an unpooled test? So the standard error goes in the denominator. Then it's life as usual. We calculate our test statistics. Since we're running a two-tailed test, we'll put the negative of it, the positive of it, calculate the p-value being the areas to the right and to the left. This area will be equal to that area, so find one of them, multiply by 2. Confidence interval, the same thing. In general, confidence interval has 3 parts. We have our estimate plus or minus our critical value from the sampling distribution times the standard error. In this situation, our estimate is just of, our estimate of mu1 minus mu2 is x bar 1 minus x bar 2. We use the t distribution. We multiply by the standard error. And again, that depends on pooled or unpooled. Do we assume equal variances? Do we not assume equal variances? And I have very, very, very strong feelings about this. It's not some, well, more about that later. So okay, cool. Now, in terms of confidence intervals, we can tell a lot about the ordering, which is bigger, mu1 or mu2, just by examining the confidence interval for the difference. If our confidence interval is negative negative, then we assume that mu1 is less than mu2, or we assume that the difference is negative. If we have a negative and a positive, then the only way that can happen is 0 has to be contained in our interval. No other way. Can't happen any other way. Then we can conclude that mu1 is equal to mu2, or the mean difference, or the difference is actually equal to 0. If we have plus plus, then we assume mu1 is greater than mu2, and that this difference is greater than 0. That shouldn't be any surprise to anyone. If we look on the number line, if we have an interval over here where the left endpoint is negative and the right endpoint is negative, or if we have left endpoint is negative, the right endpoint is positive, 0 has to be contained in there, and same argument for positive, positive. All right, I won't go into that a lot because this is a grad class, not undergrad class. Okay, finally the assumptions, the normality assumptions. What we typically do with the normality assumption, easy for you to say, and I'll demonstrate this in the next video, is we run what's called a Shapiro test. And to examine the equal variance assumption, we use what's called a Levine test. The Shapiro test has this test statistic. The null hypothesis is the data comes from a population that is normally distributed against versus data comes from a population that is not normally distributed. Levine's test starts out with the assumption that the variances in the populations are equal. Now, in our case, we're going to stop that at just 2, right? Because we have 2 populations. But we're going to move into the ANOVA family pretty soon, where we have more than 2. So in general, Levine's test can test the equality of variance k-variances. Specific to this video, we just have 2. So the alternative would be that the variances are not equal, but in general, at least one pair of the variances for some ij are not equal. Now, there's another test that we sometimes use equal variances. It's called Bartlett's test. A lot of people prefer Bartlett test. Typically, it has more power. In other words, if you hold everything else constant, it will create a lower p-value than the Levine's. So, proceed with Levine and Bartlett. Okay, no, that's on a different note. Let's stay up here. This is something completely different. So, yeah, I think it's fine either way. Again, you're more likely to reject the null with Bartlett's test. It's more sensitive. I am just a creature of habit. My doctoral professors taught me Levine's test, and I've used it for years, and it's what I use. But either one is just fine. All right, now, here's probably the most important part of the entire video. What do you know? So let's say in our situation, we test this so the variances are equal with either Bartlett or Levine's. And let's say we fail to reject. Now, this one needs to be tattooed to the brain because I file this under extremely important. Extremely important. I'm not trying to threaten anybody here. That's not the way I roll. It's not the way I teach. But if this is misunderstood, because I'm going to make it very, very clear in this video, if this is misunderstood, then a high proportion of points are deducted. We can't misunderstand this. It's too important. Okay? So if we fail to reject, so that's saying that this statement is more believable than this statement. The null hypothesis is more believable than the alternative hypothesis. Do we conclude that the variances are equal? Absolutely not. If you do, then you don't understand the basic fundamentals and framework of a test of hypothesis. Failing to reject doesn't mean this is a true statement. It just means it's more believable based on the sample data that we've collected than this statement is. Same thing. If we reject H sub O, we get rid of this, right? I don't want to mark this because I don't want to dirty up my paper, but messy. I'm gonna get my paper messy. But if we reject this, that's saying that this statement right here is more believable than that. Does that mean that our population variances aren't equal? Most likely, they're not equal. That's a more believable statement than this one, but we can't say with absolute certainty. If you start making absolute certain statements like that from a test result using inference hypothesis testing, then you need to rewatch my type 1 and type 2 error videos because we make errors. There's a 0.05 probability that this is true and we reject it. There's probably about a 0.8 probability that the null is false and we fail to reject it, right? So you did not understand errors. We can't make strong statements about an entire population, the variance of one population versus the variance of another population based on sample data. We just can't do it. Completely and totally inappropriate. So use softer language when interpreting Levine's or Bartlett's. So use softer language when you interpret any test of hypothesis for that nature or for that matter. All right, gang. Next video, we're going to dive into the weeds and show you how to write this up and report the results. We're going to get into Bartlett and Levine's and all that cool stuff. All right, take care.